speaker, Dr.R.Castillo Pérez from the Ponente Nacional, and his talk is titled The Methods of Fundamental Solutions with Bergmann kernel in Eigenvalue Problems. So, please.
Thank you very much. I would like to thank the organizers for the opportunity to deliver this lecture. As it was presented, I will talk about the method of fundamental solutions, which is a very well-known method used in order to solve partial differential equations. And here, its use for solving eigenvalue problems, which can have some difficulties or some problems. I will try to solve that introducing the construction of a reproducing Bergmann kernel. Then I will shortly talk about this method of fundamental solutions, and this was introduced in 1964 by Kupratze and Alexice, and in general it states that for the solution, for example, of this Helmholtz-Dirichlet problem, that a solution U for this problem, given these boundary conditions for a point P which belongs to this domain omega, which is boundary simply connected bounded domain, which can be in R2 or for this example, it can be in R2 or R3, and for this example is in R2. Then in this, for this point in this domain, the solution fulfilling these boundary conditions is stated as a linear combination of fundamental solutions, where these fundamental solutions are represented by these psi functions, and these functions are based in fundamental solutions. In this case, the fundamental solution is the Hankel first type of order 0, and is based in this parameter lambda, which is some scalar, and the solution is constructed using some other domain, which is denoted here with this omega tilde, which is having this omega domain inside, and for which the boundary is denoted this way. So the points Q, which participate in the construction of these solutions, these fundamental solutions, is with points Q distributed along this boundary. So this boundary is usually called some virtual boundary, and in this case, the points P in here and the points Q in this boundary help to construct a system of solutions, and then this Qj will be called also singularities on this boundary, and the coefficients Aj are to be determined from the boundary conditions. So from this set, you can see that we will use a certain number n of functions in order to construct this solution. Now, this is a general method for solving boundary value problems. But in the case of eigenvalue problems, what you have to change is that the method will construct these solutions and use their determinant from a linear system, which will be used to get these solutions. So for two special cases, which are circular domains and rectangular ones, the solutions exist in an analytical way. So it is very easy to compute this kind of solutions for the eigenvalue problems in those geometries. But in the cases of non-trivial geometries, you have to use numerical methods. In the case of numerical methods, then no analytical solutions are available in most of the cases. Then you have to use some methods, and one of them is you use a set of collocation points where you get these points Pm, m going from 1 to n1, and a set of sources which are points Qj going from 1 to n2, and from these two sets of points you construct the solutions. The solutions for homogeneous linear system of approximate solutions of equation 3, which was this one, this form of the solutions. Then with this homogeneous linear system, its complex determinant will vanish at the eigenvalues of the problem. So it is very easy to deal with this method. It's a very accurate method. It is not demanding computation in terms of the computation that it requires for the computation of the eigenvalues. It's very simple. But one of the drawbacks that this method has is that since it is based on the determinant, it should use a higher number of functions in order to compute eigenvalues with an increasing value. So I can show, for example, for the case of a rectangle, how the determinant behaves. Here in this case you can see that for 15 functions the determinant is like this one. So the little deviations in the curve show the presence of the eigenvalues. Here the eigenvalues are shown with these gray lines, and here you can see that the determinant for 15 functions, it's not so easy to check the occurrence of the eigenvalues. So you need to increase the number of functions, which in this second case, in the red curve, is 45, in order to find the eigenvalues with a better opportunity not to miss any of them. And as you can see, when you approach a larger value of lambda, then it is harder to find these eigenvalues. So you should keep increasing this number in order to find the eigenvalues for larger values of this spectral parameter. But one of the main problems is that this eigenvalue that we get from the determinant has a very, very low value. So here we are talking to 10 to the minus 300. And this value is very, very small. So here you can see, for example, that for the case of 75 functions, the graph is even outside this figure. And here you can also check that the value tends to increase. So in this area, it will also become harder to find the eigenvalues. So with these problems in mind, here the problem that I present is a simple one for the rectangle with this definition, and for the Dirichlet eigenvalue problem. So what we propose is to use some other method. And some other methods have been proposed before. So the use of finite differences method, finite element method, boundary element method, and even the method of fundamental solutions with some variants. These variants include the so-called singular value decomposition, Burton and Miller method, and also some meshless methods, which use radial basis functions or the method of particular solutions. So these methods are more or less complicated. They state some rules, for example, for the location of the points in this virtual boundary. Some of them require of high computation times and so. And here we propose a simple but at least we think efficient idea. And it's the following one. It is to use the so-called Bergmann type reproducing kernels. What are these reproducing kernels? Well, if we consider this equation here, where Q and U are complex valued functions with Q continuous in the closure of the domain, then we define this linear space of complex solutions by sigma alpha for solutions having this behavior, with alpha being here from 0 to 1, and P and Q 2 points in the plane, such that P belongs to the closure of the domain and Q is a point of the domain. So, Bergmann kernel we introduced in this paper, and the main result is represented in the following theorem. So, for the space, sigma 0, I will equip it with one of the following scalar products. So, in one case, the one scalar product that I will denote with subindex 1, defined this way, with this bar stands for the complex conjugation, and the second scalar product that I will denote with subindex 2 here, and which is based in normal derivatives for these functions u and b, and here also bar stands for complex conjugation. And under these scalar products, it is possible to find a couple of reproducing kernels. These reproducing kernels I will call F for the scalar product 1, and it will be useful for solving Dirichlet problems. And the second reproducing kernel I will denote with M, which will be based on the second scalar product, and which will be helpful for Neumann boundary and eigenvalue problems. So with these definitions for the scalar products and the kernels, so now this theorem that was established in this work says that if Q is a continuous function, complex valued, and in omega, in the closure of omega, and these sets phi j, an infinite set, a complete system of functions in sigma 0 with respect to this norm based on the scalar product 1, orthonormal with respect to this scalar product, then this series here of the products of such functions from this system of orthonormal solutions, then this series converges to this Bergmann kernel F in the norm generated by scalar product 1, and uniformly and on any compact subset of omega. Then this gives us a way to compute F based on these functions, and we need these functions then a complete set of functions in sigma 0 with respect to this norm. So for this Bergmann kernel, we get a very useful property, which is the following. Reproducing property will behave like this: the scalar product 1 of solution U evaluated at point P times Bergmann kernel F of points P and Q will give the value of solution U in point Q. So you can remember that P was established for the closure, so it can be in the boundary, and U is a point in domain omega. So you can use it to construct the solutions from the boundary to the interior domain. But here is not the more important property, but the one that we are interested in is that if we consider for this Bergmann kernel F, the solution and this kernel as a function of the spectral parameter lambda, then it is possible to compute the zeros of the inverse of this Bergmann kernel evaluated at 2 points P0, Q0, which are arbitrary fixed points in the considered domain. And these zeros of this inverse of the Bergmann kernel will coincide with the singularities of this Bergmann kernel, and then we'll give the eigenvalues lambda n of, for example here, the Dirichlet problem. this, to the difference of the previous example that I showed with the determinant, will give us a graph which is like the following one. Oh, sorry, I should explain the method first. Then here we choose some range of values for lambda, which is going to be evaluated for the occurrence of eigenvalues. For example, we can say an interval between 3 and 25 and see how many eigenvalues are there. Then an internal point is chosen. This internal point is an arbitrary point, so I can choose any point. But sometimes it can be an unlucky choice if this point coincides with the location of an eigenvalue. So in these cases, I should try at least a couple of points in order to avoid one location in which some eigenvalue will not be found. If I have this bad luck to locate a point somewhere where an eigenvalue will not be found, then choosing a second point, arbitrary one, will help to get this point. Then a set of points is established for PM here in the boundary of omega, and Qj for the virtual boundary for omega tilde. And from these points, the fundamental solutions are computed. From this set of fundamental solutions, we apply the Gram-Schmidt process in order to orthonormalize the system. And then for the functions obtained in this way, after Gram-Schmidt process, then it is possible to construct the Bergmann kernel. This Bergmann kernel will give with its inverse, its zeros will give us the eigenvalues. So as I said, in this case, the graph is completely different from the ones that I showed with the determinant. In this case, you can see that the scale has a maximum of 10 to the minus 20, and it is never reached. Usually the lower that this cube will get will be 10 to the minus 15, so machine precision. And here you can see that the occurrence of the eigenvalues is very, very well established here. It is very easy to locate the eigenvalues here. Again, the lines correspond to the presence of the eigenvalues, which in this case can be exactly computed. And you can see that, for example, here, for values as big as 25, these eigenvalues are in general behaving very well. You can see at the end of the graph that this behavior is not always so good. You can see some places, like for example here, or for example here, that this occurrence of eigenvalues is not so easy to see. But if you change the point that was used, Q0, as an arbitrary point inside the domain in order to compute this graph again, then some of the cubes change. And for example, we might expect that this one that was hard to find with the previous choice, that for example in this case was this one, would be easier to find with another choice of point. I should say that the process to look for the eigenvalues is dividing the range in which the values of lambda are looked for in steps of, for example here, 0.01, and for these steps, one proceeds to compute the Bergmann kernel in each point. Usually we have two options for this. One of them is to establish a pre-assigned precision for the computation of the Gram-Schmidt orthonormalization process. We know that functions after Gram-Schmidt process should be orthonormal, and then their product when they are different should be zero, and the product of a function with himself should be 1. So from those products we can get some error in the computation of this process, And we can use that as some way to establish the precision of the computation. So for this example, in the rectangle, the Gram-Schmidt accuracy was established as this one. The arbitrary point was established like this one, and the number of functions used to compute the eigenvalues are in the range of 31 for the slowest eigenvalue to 78 for this one. So you can see another advantage of this method, that the number of functions that we use is very competitive comparing with the methods of fundamental solutions alone. And then I can show another result, which is analytical solutions, which is unitary disk. Here I show more for the elements for the computation, so the solutions will be Bessel functions of the first kind of order n. Those will give me the series of these functions will give the eigenvalues. I can establish Gram-Schmidt process precision in 1 times 10 to the minus 12 steps of 0.01, and the number of functions used to compute the eigenvalues was from 28 to 68. I forgot to mention that there is some distance between the virtual boundary and the original boundary, and that distance has some relevance in terms of the precision for the computation of the eigenvalues. So, but the values are usually less than 1, from 0.3 to 0.7 in the cases that I've shown. For example, here I should say that with 160 points per unitary length, which are used for the computation of the contour integral, which defines the scalar product, then we had from a list of 76 eigenvalues in the first arbitrary point that we chose, we could obtain almost 50 of them. And with the second step, using a second arbitrary point, we could complete the list of the first 50 eigenvalues. So in some cases, some of them are missed. Then changing to another arbitrary point will help to get them. And in some cases, they don't appear until you use a shorter step for looking for these eigenvalues. So here, since I'm using higher precision, then I obtained some absolute error or relative error, which are in the order of 10 to the minus 8 or 10 to the minus 9. And I have to say that here the computation time was long, of 18 hours. In the previous case, when you fix the number of functions to follow some linear increase, then this time can be reduced to half an hour, but you're losing the precision. And let me show the graph for the relative and absolute errors in the computations of eigenvalues for this case of the unit disk. And you can see that their behavior is more or less bounded. So the error will not increase when the number of the eigenvalue increases. So as I said, here was a set of 76 eigenvalues. So those were two tests against geometries which have analytical solutions. So what happens when one considers some non-trivial geometry? And here I can show an example of the so-called isospectral drums, which were used to answer this question of, can you hear the shape of a drum? And the answer is no. Two different drums may have the same set of eigenvalues. These two are one of that case. And here, for both geometries, we have the same list of eigenvalues. So here I write down the list of known eigenvalues for these geometries, these domains, and for each of these spectral drums, we computed using our method, and we could see that it is possible for us to find the same eigenvalues with an error of 10 to the minus 3. We are still trying some improvements for this precision, but I hope that this method will be very stable, accurate, and somehow maybe will be fast in the future. So that's all that I wanted to say. Thank you very much for your attention.
Okay, well, we have time for several questions. Anyone has any question, comments? Please.
Yes, I wondered about cheap boundary conditions. If you have a function, you define some part of the boundary, but the other one you have to deliver. I can see that the net product that you define is important to the boundary condition, but in those cases, you have an alternative method, or can we use also to frame those problems?
Yes, theoretically it is possible to do it. We have not done it yet, but it is possible to mix boundary conditions, yes.
Is it possible to extend to homogeneous homogeneous unconnected surfaces?
For inhomogeneous, I suppose yes. We have not tried it yet, but I suppose yes. For not connected, I'm not sure.
And those new condition, as I think maybe I would understand this. In terms of condition, C2 interior, one mass alpha and but you can have three angular points which don't satisfy this condition.
Yes.
I understand.
Yeah. In this case, we also choose rectangle and this kind of geometries because of the presence of these angles, but they seem not to affect the performance of the method. For the case of I showed here for the case of Dirichlet eigenvalue problem, but if you move to Neumann, then the condition can be changed. Instead of this set sigma 0, let me see. Yeah, instead of this sigma with 0, here you have alpha with a value greater than 0. Then you increase for the case of Neumann here. I'm not sure if that was your question.
But the angular point not satisfies this condition.
In some of the methods.
This is the Lipschitz boundary. So
yes. Yes. In some cases, you establish these points. You try to avoid these points.
This is something with finite arrangements.
I'm not sure that I understand, but in some methods, these corner points are avoided, just not to have this participation in the construction of the solution. But here we use them, and they seem not to affect the numerical implementation of the method.
What condition is satisfactory for the Bergmann construction of the Bergmann kernel? What's the boundary?
Yeah, well, the
It is a smooth boundary, maybe
Yes.
it's enough for the boundary which has this.
we have continuity of Q and U. We have this condition for solution in this way. And also, we should avoid some points. The location of P and Q is also important, but any other conditions we don't have.
Okay, so any other question? Okay, if not, let's thank again the speaker.